Hey guys, today we are going to talk about work, okay? And so this is a lesson that goes from super simple problems to really difficult problems, depending on what you're doing. So what is the definition of work done by a constant force? Okay, so if an object is moved a distance d in a direction of an applied constant force F, then the work done by the force is defined by W equals F times D. Work equals force times distance. Okay, so actually let's just write that out. Work equals force times distance. Okay, so those are the easy problems. There are four different types of forces. There's gravitational, electromagnetic, strong nuclear, and weak nuclear. And each of them kind of has their own formulas that they work with. A force can be thought of as a push or a pull. A force changes the state of rest or state of motion of a body. For gravitational forces on Earth, it is common to use units of measure corresponding to the weight of an object. So what they're saying is on Earth, the weight and the mass are the same thing. Okay? All right, lifting an object. So determine the amount of work done by lifting a 50-pound object 4 feet. All right, this is really simple. So this is simply work equals force times distance. So work is going to be 50 times 4, which is 200, and it's measured in, wait for it, foot-pounds. All right, you should never get a problem like that wrong. Very simple. Okay. In the U.S. measurement system, work is usually expressed in foot-pounds, inch-pounds, or foot-tons. In the international system, the basic unit is the Newton. So you probably, if you're in physics or if you're in physics, you probably heard of newtons. That is the force required to produce an acceleration of 1 meter per second on a mass of 1 kilogram. Work is typically expressed in terms of Newton meters called joules. In yet another system, the centimeter gram second system, the basic unit of force is the dyne. The force required to produce an acceleration of 1 centimeter per second on a mass of 1 gram. In this system, work is typically expressed in dyne centimeters, which are called ergs, or Newton meters called joules. All right, now, what about work that's done by a variable force? So the first problem we did was a constant force. It was something that weighed 50 pounds, and we simply moved it 4 feet. Okay? But that's not the way most things are done. So work done by a variable force. So in example 1, the force involved was constant. When a variable force is applied to an object, calculus is needed to determine the work done because the amount of force changes as the object's position changes. So the best example of that, or one of the easier ones to understand, is a spring. Okay, so you take a spring and you want to push the spring so it contracts or compresses, but the more it compresses, the harder it gets to compress it. That's a variable force. If an object is moved along a straight line by a continuously varying force f of x, then the work W done by the force as the object is moved from x equals a to x equals b is given by the work is the integral from a to b of f of x dx. Okay, so 3 important laws of physics you need to know. Hooke's law. The force F required to compress or stretch a spring within its elastic limits. So what that means is if you compress it or stretch it too much, it just breaks. Okay, is proportional to the distance d that the spring is compressed or stretched from its original length. That is, F equals K times D. where the constant of proportionality K, the spring constant, depends on the specific nature of the spring. So generally, the thicker the spring, the stronger it is. This K is going to get to be bigger and bigger and bigger. Okay. Then you got Newton's law of universal gravitation. The force F of attraction between two particles of masses m1 and m2 is proportional to the product of the masses and inversely proportional to the square of the distance between the two particles. So that is F equals G times m1 times m2 divided by d squared. m1 and m2 are in kilograms and d is in meters. F is in newtons for a value of G equals 6.67 times 10 to the negative 11 power cubic centimeters per kilogram second squared. Okay, so G is the gravitational constant. And that would be on Earth. That G can vary depending on how strong the gravity is. When you're, okay, so also keep in mind the inverse square law applies here. That's the divided by d squared. So with gravity, if you double the distance that you are from an object, then you only have 1/4 the gravity. If you triple it, you have 1/9. So you're taking the distance and you're squaring it and you're dividing by that number. Coulomb's law. The force F between two charges, Q1 and Q2 in a vacuum, is proportional to the product of the charges and inversely proportional to the square of the distance between the two charges. So F equals K times Q1 times Q2 divided by d squared. So this works very, very, well, virtually exactly the same as that one, except it's electrical charges. Q1 and Q2 are given in electrostatic units and d in centimeters. So F will be in dynes for the value of K equals 1. So let's look at this example here, compressing a spring. Okay, so we're going to use Hooke's law. And we know that F equals KD. Okay, so we have to figure out what K is here. So a force of 750 pounds compresses a spring 3 inches from its natural length of 15 inches. So here's what we know. We know that it takes a force of 750 pounds to compress it 3 inches. So D is going to be 3, and F is going to be 750. And so we can solve this, and we figure out that K is going to be 250 when I divide both sides by 3. So this tells me that F is 250 K for this particular spring. Now, I'm sorry, D, not K, D. All right, so then find the work done in compressing the spring an additional 3 inches. Okay, so the amount of work then is going to be the integral from 3 to 6, okay, of 250 x dx. Now, why is it 3 to 6? Well, remember, this is variable. So I've already moved it 3 inches because it told me it takes 750 pounds to spring 3 inches from its natural length. Okay, so as I compress it from 3 to 6, it's going to take more work to do that. So this is not a bad one to figure out. This is a pretty easy one to set up, which is generally the hardest part. Setting up the problem is the hard part. After that, it's pretty easy. So W is going to be 125x squared evaluated from 3 to 6. Okay, and then we're just going to plug in our 6 there and plug in our 3 there. And 125 times 36 is 4,500. And 125 times 9 is 1,125. And we subtract those, we get what, 3,375. And this is in inch pounds, because we were moving it in inches, and it was pounds of pressure. Okay, so not too bad of a problem right there. Definitely more difficult than the first problem we had in calculating work. Okay. Now, example 3, moving a space module into orbit. Okay, so this one's going to have gravity involved in it. The space module weighs 15 metric tons on the surface of the Earth. How much work is done in propelling the module to a height of 800 miles above the Earth? Use 4,000 miles as the radius of the Earth. Do not consider the effect of air resistance on the weight of the propellant or the weight of the propellant. Okay. So here's the deal. We're going to start out with this formula. F equals C over x squared. Okay. There's F. It's going to be 15. And we got to figure out C. And X is 4,000. Okay. Why is that 4,000? So gravity is actually, the force of gravity is actually measured from the center of the object that has the gravity. So in this case, the center of the Earth, where something would weigh the most. Then as you move away from it, the inverse square law applies. So if the radius of the Earth is 4,000, I gotta have 1 over 4,000 squared to calculate the weight. Okay, so this comes out to be what, C over 16 million equals 15. And then I would multiply both sides by 16 million, and I would get, what does that come out to be? 240 million. Uh-oh. C is 240 million. Okay. Now we can figure out the work. So let's take all this, move it over here, give us a little bit more room to work here. Okay, so now the work is going to be the integral from a to b of f of x dx. So, then my work, or my formula, is going to be, now if I want to put this thing 800 miles above the Earth, I need to find the integral from 4,000, because it's already 4,000 miles above the center of the Earth, to 4,800 miles. Okay, and since C was 240 million, this is going to be 240 million over x squared dx. Okay, here's my formula right here that I'm going to integrate. So I figured out the constant C. Okay, and we could probably be best to rewrite this as 240 million x to the negative 2 dx. Okay, so I'm going to integrate that. And that's going to be, let's see, x to the negative 1. It's going to be negative 240 million x to the negative 1. Evaluated from 4,000 to 4,800. Okay, so I'm going to go ahead and plug in. You know, let's just take this and factor it out to the outside. And we'll we'll do this in here. So this is going to be 1 over 4,800 minus 1 over 4,000. And if I subtract that and multiply by this, I'm going to get 10,000. And that is in mile tons. Now, why is it in mile tons? Because I moved it 800 miles, and my unit of measure and weight was metric tons. Okay, so again, that one was not too difficult. Okay, now this stuff can get difficult pretty darn quick. So this is one of the tougher ones right here. You're going to empty a oil tank. So here's the deal. You got a spherical tank of radius 8 feet, is half full of oil that weighs 50 pounds per cubic foot. So let's sketch a picture here. We've got this spherical tank, okay, and it's half full. Colored outside the lines there, that's unfortunate. Okay, and it has a radius of 8 feet. So that's 8 feet right there. And the oil weighs 50 pounds per cubic foot. So find the work required to pump the oil through a hole at the top of the tank. So right here, we've got a hole up here at the top. Remember, this is 8 feet also. And then this would be a height of 16 feet right here. This would be a height of 0. Okay. So here we go. So the change in force is going to equal the weight. Okay, and it's 50 pounds per cubic foot times the volume. So that's the weight of the oil that we have to move. Okay, so it's 50 pounds per cubic foot, and so we have to figure out how much the weight is. Okay, so we got to figure out the volume. So let's see. Okay, now what we're going to do here before we go on is we're going to think of this like this. If we go up a certain distance from the bottom of this thing, we'll say y, then we get a circle, okay, and it's got a radius right here, okay, and if we think about this as stacking a bunch of discs on top of each other, okay, where the thickness of this disc is delta y right here, then we're going to lift each one of these discs up to the top and get it out, okay? So what we need to do then is we need to figure out what the volume of each one of these discs is. So the volume, since it's a circle, is going to be pi r squared. So this is going to be 50 times pi times the radius squared times the height of the disk. Now the height, we call it delta y. So we're going to put delta y in there. And we just have to figure out what the radius is. Okay, so we're going to call this, we call this that for right now. Now, we have to figure out what the radius is, and the radius depends on how far from the bottom of this tank we are. So we're going to take the equation for a sphere, which is going to be x squared plus y minus, I'm sorry, not a sphere, a circle, equals 8 squared. So we've got, this is the equation for a circle with a center at 0, 8 and a radius of 8. So that's going to be the equation of that circle with that center right there. It's going to be this green circle right at the top. Okay, so x squared, this is y squared minus 16y plus 64 equals 64. And then we're going to solve for x. So if I subtract the 64, that goes away. So this is going to be 16y minus y squared over here, which we're going to square root. Okay, there's my x. Okay, now remember, a disk that is y feet from the bottom of the tank has to be moved 16 minus y feet up to get it out. So, for example, if this is 2 feet right here, then I got to move that disk 16 minus 2 feet to get it to the top. Okay? So, in our formula that we have, where the work is going to be the force times the distance, okay, then the force is going to be 50 pi times x, but we figured out that's the square root of 16y minus y squared times delta x, which is going to be 16 minus y, because that's how far we have to move. We have to move that 16 minus y feet. Okay, now let's clean this up a little bit. So if I square this, it's going to be 50 pi times 16 minus y squared times 16 minus y. And if I multiply that out, I get 50 pi times y cubed minus 32y squared plus 256 y. Oops. Okay, so then we're going to delta y. So now we're going to integrate that. So the work is going to be, I can take this constant outside here, and we're going to integrate from 0 to 8, y cubed minus 32y squared plus 256y dy. All right, integrating, not a problem. So this is pi times 1/4 y to the 4th minus 32/3 y cubed plus 128 y squared, evaluated from 0 to 8. Okay. So we'll go ahead and plug in 8. And then we would put in 0, but that's just going to be 0, so just go minus 0. Okay, so 50 pi, this is 1024, I think. Minus 5,461. 0.3 repeating. Plus 128 times 64 is going to be 8,192. Okay, and that comes out to be 589,781.6 repeating, and that's measured in foot-pounds. Okay, again, the integrating is not the problem. It's getting the problem set up that's the difficult part. It's this part up here, and knowing what it is that you have to integrate. Okay. Next example here. So, oops, I didn't turn the page there. Lifting a chain. A 20-foot chain weighing 5 pounds per foot is lying coiled on the ground. How much work is required to raise one end of the chain to a height of 20 feet so it's fully extended? Okay, so if you've ever tried to do this, chains are super heavy. Pick up a chain, it gets harder and harder to lift because it gets heavier and heavier as you go. Okay, so we're going to have to figure out, delta F. It's 5 pounds per foot. And then we got to move that thing, whatever the length of it is, right? Okay. So this is just 5, and this is going to be delta Y. Okay. Now, delta W is going to be the force increment F times the distance that it's got to be moved, right? Okay, so in this case, it's going to delta W is going to be 5 delta Y times Y, which is going to be the length of the chain. Okay, so that's just 5Y delta Y. So we're going to integrate that. We're going to integrate from 0 to 20. 5y dy. So that's easy to do. That's going to be 5 halves y squared evaluated from 0 to 20. We're going to go ahead and put 20 in there. .400 times 5 is 2,000 divided by 2. That should be 1,000 foot-pounds. And we're done with that one. So that one wasn't too bad. Okay. So here's your assignment. You got 7 problems. Give it a good shot. And you're going to do 1 and 3. Those shouldn't be too bad. 5 and 9. 5 shouldn't be too bad. 9 shouldn't be too bad. 13, 21. Let's get a little bit harder. Okay, so remember, when you're integrating things moving above the Earth, you want to integrate from 4,000 miles, which is the radius of the Earth, to whatever it is that you're going to do. All right, I will see you next time. Have a great day.